Good afternoon, this is Schweitzer, and this is a little initial conversation of impulse and momentum. A couple things you might note here is, again, one of Newton's laws of motion is force equals mass times acceleration. So if we apply a force to an object, per se, this mass will then start to move. That movement would be a form of acceleration and also a form of velocity change. Acceleration would be included as the change in velocity over the change in time. So we might be able to take this quantity and sub it in for here, and we get the force applied on an object will cause the mass of the object to change velocity over a certain amount of time changed. And in this point, this amount right here is called your linear momentum. Now, momentum is symbolized by P equals the mass times the velocity. Of course, anytime if the momentum is being changed, then a force must have been applied. I guess you could apply a force that doesn't cause any movement, and therefore there'd be no change in momentum. But if you have a change in momentum, that means you would have had a force applied. So a force change in momentum might be described as momentum final minus momentum initial, which of course would then be the original mass times the velocity final minus the mass times velocity initial. Okay, you could factor this out. The mass is velocity final minus velocity initial equals your change in momentum. Either way, we have some amount of change in momentum. One more common idea of this is, okay, I'm going to take my equation and I am going to apply a little bit of algebra here and say force. I'm going to move my change in time here to here. Time equals mass times velocity. I'm going to keep my change on here. Now again, different ways look at it differently, but this is a pretty common idea. So for this is called this right here is called impulse. Another way of describing how much, you might say, energy is being applied to something. So if you take let's say a ping pong ball or a baseball, and you take a bat or a stick and you whack it with this thing, okay, then this guy is applying an impulse, which is going to then cause the ball to change velocity. And by changing velocity, you are changing your momentum. So impulse causes a change in momentum. Impulse, letter I, is equal to the force applied on an object over the course of time. And this will cause a change in momentum, which is equal to the mass of an object times its change in velocity. Okay. Now again, let's look at this idea of impulse, and this is called this in the box is called impulse momentum theorem. Okay, pretty useful idea there. Now, this idea of applying an impulse to something is essentially you hit something. If I were to, let's say, hit this ball right here, okay, and let's just say hypothetically that it was sitting on a desk, I'm looking face down on it, balls look right here, and on this desk I have a post right here, and I have a post right here. These two are rock solid posts. Do not move. As opposed to another scenario where I have a ball, same ball, just sitting on the desk, and this guy here, this bat, is free to whack the ball. Now, what you probably don't even realize as you hit something is that you automatically, as you hit something, to some extent, you follow through on your hit, and the ball is hit for a very large, well, relatively speaking, period of time. So do a little thought experiment. Imagine yourself just taking a stick or a bat and whacking a ball off a desk. Now let's imagine again on this side, where you only get to hit the ball until this period, because then at that point it's stopped by the stick is stopped by stationary blocks. At this point, again, a nice mental experiment here, you would realize that this ball only comes off with some amount of velocity, whereas the velocity of this ball ends up being much higher. And why is that? Even if you apply the same force to both objects, okay, this ball manages to come up a lot faster. And that's because as you apply a force, the time over which that force is applied causes the impulse to be given. Make sense? Okay. This impulse therefore causes a change in momentum. And since the mass of both balls are the same, we get a larger reflection in change in velocity. This idea, now we could go through the math on this. I don't know, I'm not sure if I will in this quiz or not, but this is usually our first quiz that I would give. A first concept, would just be what happens here. Okay, mathematically, algebraically, you should be able to, given 3 of these 4 variables, I can solve for the missing variable. So that's not too bad. But in this case, let's talk about a couple more just general examples of where impulses and change in momentum occurs. Okay. Now, let's say, for example, you are doing a pole vault. Okay. And you have your large little stick here, and you have let's have them run to the left. You have a little stick guy, and they got their little pole, and they're running, and then they stick it in here, and they fling themselves over the top of this thing, okay, and they land on this nice big thick mat. Why do we need the mat? This person, just before they hit the ground, has a certain amount of velocity. Let's call it VI. And then when they come to a rest here on the mat, they'll have another velocity. Let's call it VF. So the person's change in momentum, whether the mat is there or not, is going to be the same. It would go the mass of the person times the velocity final minus the velocity initial, and regardless of whether that mat's there or not, they'll have the same change in momentum. They're going to go from some speed to stopping. What's the point of the mat? Well, in this case, if you have the other half of this thing, the impulse side of it, equals the change in momentum, which we know this will not change, but the impulse is the force applied times the time equals a change in momentum. So now this is a sort of a static quantity. So as the time increases of the collision, the amount of force required is minimum. And of course it only requires depending on the person, a certain amount of force that is required to, let's say, break a bone or cause a concussion of some sort. So if we can increase this time, we can reduce the amount of force, and therefore the person doesn't feel as drastically the change in momentum. Okay? This also occurs, let's say, in something as simple as a wrestling mat. A person is tossed onto a wrestling mat, so person A and person B are wrestling. Let's go A and B. Let's say B grabs A and somehow through the magic of physics tosses A, and they land flat on a mat. Now, if this were to happen, let's say in the cafeteria at school, that would be quite drastic. That person would have a hard time getting up. Okay? But happens after school on the wrestling mat, and it happens on a mat that is sometimes maybe only 1 inch thick. And if you're using a Greco-Roman mat, it might be as much as 3 inches thick. Okay, so what's the point? Again, all you do is increase the time. Force times time equals your change in momentum. Very easily. Another example of this, okay? You would take a person who is standing at a desk. Every single person knows this. You don't have to be taught this. You jump off the desk, you land on the ground, or even, let's say, a person jumps off the edge of a house. Maybe it's burning, or okay, and they have to get off. This person would stand their legs and then immediately roll to the ground. And they're trying to increase the amount of time that they have to experience this change in momentum. This person might, from a desk, might just, when they hit the ground, they might just bend their knees as much as possible in order to increase the amount of time that they're going to experience this jump. If you were a little kid and just joking around, maybe you'd want to try and jump off and hold your legs straight. You'll notice the difference. Don't allow your knees to bend. It jolts right through your back. On a more serious note, we also have things like car crashes. Okay, car crashes and engineers. Every time there's a car crash, every engineer is trying to save the life of the driver. Okay, all they're trying to do. Well, there's probably two things I would say. One, they're trying to increase the surface area of a collision, because the surface area is going to force is equal to force divided by area equals pressure. So they're trying to reduce the pressure. All comes down to force applied to a human being. But on this topic of this chapter, we're trying to force times time equals a change in momentum. An engineer is trying to increase the time of the collision and or possibly release some energy in different ways that might not be affecting the crash then. A couple of ways. One is a seat belt. Seat belts will definitely stretch. They are not, they don't make a seat belt for, say, out of metal. Okay? Imagine if you had a wire or a metal seat belt. It would cut you in half. That force would be too big. They use fabric here, and that fabric stretches. So much so that sometimes seat belts aren't reusable. Once you're in a crash and a seat belt is broken, it often has to be replaced. Next one is crumple zones. Again, as a car crunches in, it increases the amount of time over which that occurs, especially if you have another car that's also crumpling. You may notice over time in your life, when you see tragic accidents, a car hitting, let's say, another car is not nearly as bad as a car hitting, let's say, a tree. Trees are quite unforgivable. They do not bend, and they don't break. Therefore, the amount of time occurring over the course of this particular impact is very small, which then causes a very deadly hit for the car. Now, anytime you have a collision, you have a force that's applied. Now, whether that force applied is a car hitting a tree, person hitting the ground, anything, it's not a very consistent force. You may even say it's the force average. This force is happening over time. It's not like, if we were to graph it, it's not like all of a sudden you got force versus time, that all of a sudden at time A, if you were to hit somebody in the face, at time A, the first little smidgen of your hand touches the person's face, or wherever you decide to punch them in the arm or whatever, and then continues on, and then at point B, or you release contact with that person. and this is the force. Unfortunately, that is not what happens. You would note that if you were to slow it down, that in fact the initial contact with the individual, or if it's a car crash or even a ball bouncing, the first contact is very small, and then it builds, and then it goes like this. You should be aware that this might be considered the force average, the average force. And you should be aware that this area underneath here is the impulse. Okay? So I could, by chance, have the same amount of impulse. You remember, impulses cause change in momentum. I could have something at point A, and I'm going to go, here's point B, and I'm going to go all the way out to point C. I'm going to have this occur. Okay? At this point, I may have the same amount of impulse, but my measured amount of force is just smaller. And that can have very impactful results. Okay? Again, probably from here, the biggest important thing we got is this right here. Solving problems using force, momentum, impulse, and time. Thank you very much. It's Andy Schweitzer.